Hello everyone, this is Luboš Pirkl from CFD Support, and I would like to welcome you to the webinar where we would like to show you how we think we should simulate acoustics in TCAE software or anywhere else. So let's do that. So it's a quite broad topic. There are a lot of details to say, so let's do that. So again, the webinar is going to take about 1 hour. I'm here with my colleague Radek Máca. Let's check it. So hello, Radek.
Yeah, hello, Luboš, and hello to the audience. Yeah, I'm here and live.
Okay, that's great. That's great. It's great to have you here. It seems everything is working well. So yeah, let's go straight forward to it. I'll just mention that the webinar is being recorded and it will be made later publicly available on our YouTube channel. There will be 3 parts. In the first part, I'll make it as quick as it is possible. So I'll say just the general information about the company and the product. Then Radek will, and it will be the most practical part. Radek will show hands-on experience with the software and what to do and what not to do, and he will show the methodology. And in the last part, there will be Q&A session dedicated to your questions and our answers. So feel free ask your questions. Ask them anytime during the webinar. I think you're smart. You will find a window in the GoToWebinar client and ask your questions, and we will answer all the questions. The most representative questions will be answered right away in the webinar. The specific questions will be answered later via email, but you can be sure that all the questions will be answered because we are engineers and we never leave anything behind. We think about everything, and that's why we can do what we do, which is very challenging field of CFD. And together with acoustics, believe me, it's really challenging. I would say a big and difficult and broad topic. I guess you know it, but still you have to have everything done perfectly, because CFD is just the entry data. I mean, perfect CFD data is just the entrance to the world of acoustics. So it's relatively complex because there are a couple of stages you have to, and you have to much be pretty successful on every stage. So that's why it's so difficult. Okay, so I'll go just quickly for it. So there will be a couple of webinars still this year. So there will be a webinar on wind turbine simulation in 2 weeks, and in another 2 weeks there will be blood pump CFD, FEA, FSI, and optimization webinar, the last webinar of the year in somewhere around mid-December. And yep, so I guess you know, but still, CFD Support is the company. We are located in Prague, Czech Republic. We are 15 years in the market, and we deal with engineering simulation, especially with CFD, computational fluid dynamics. And on top of that, we do also structural analysis, FEA and FSI. We do quite a lot of optimization stuff. And today's webinar is about acoustics. Acoustics is our very favorite field because not every company does acoustics, simply because it's quite high level, and a lot of skills and experience have to be involved. Otherwise, it leads completely nowhere. So it's really high-end application, and we will show you how to do that in today's webinar. By the way, something tells me that, Radek, maybe we should switch the cameras off, right?
Okay, I didn't want to interrupt you because you look pretty great when you speak.
Oh, sure. Thank you, Radek. Thank you.
But yes,
we will disappear. We will disappear for a while. I believe that the aspect ratio of the recording will be so much better. So yeah, I'll go back to my presentation. So we deal with engineering simulations. And our flagship product is TCAE, which is a comprehensive simulation environment. We were developing it for 15 years. We have put in it all our experience with consultancy projects, or our skills, or our knowledge, or our passion, and we have dedicated so much effort, put it into the package, and we believe that our users and our clients and our audience is receiving the best possible. We have TCAE consists of several modules. Those are software modules. Users can decide to use them or not at all. There is, for example, a module for meshing. There's module for CFD, and in today's webinar we will talk quite a lot about the module for acoustics, which turns the CFD results, transient CFD results into the acoustic data, which can be further investigated, and engineers can make decisions based on them practically. Yeah, there are other modules. I'm not going to comment them at the moment. TCAE is extremely flexible because its users can use particular software modules to create their own workflows. So TCAE can be used together with in-houses. It can be used together with open source or with existing commercial codes. TCAE is still here to work and cooperate with other software pieces, and that's why it's so flexible and usable. It's completely unlimited. That means it's for enterprises, and enterprises just purchase one license, and they have no limitations on number of its users, jobs, cores, hardware installations, sessions, nothing, no limitations. It's really completely unlimited, and that's why it's so successful. It's based on open source. This is really important stuff. We are a relatively small company. We acquired a knowledge and I would say the ability to use the open source software existing anywhere globally available, and make a comprehensive package from it, which works, which is tested, which is stabilized, and all the software pieces communicate perfectly. And we use open source. For example, for CFD, we use OpenFOAM. For graphical representations, we use ParaView. For structural analysis, there's Calculix, and there are other and more. There's, in fact, there's more than 60 open source pieces in TCAE. So a lot of open source there. And on top of that, we have spent more than 50 many years in the team development aggregated here at CFD Support to make it usable for the engineers and for the industrial cases. That's important. It's not just a few academic cases, but it's for real industrial cases like turbo machinery and external aerodynamics. These two fields are extremely important. So we develop TCAE for specific applications to be really usable, to be like really high-tech, high-end top applications, for turbo machinery applications, rotating machinery, and external aerodynamics. TCAE is perfectly automated, so it can be used as a black box if the users wish so, or it can be used as a highly sophisticated research tool if needed. So all the options are open. There are a lot of options regarding the usage of TCAE. So TCAE can be run on laptops, it can be run on desktop computers, it can be run on PCs, clusters, clouds. It can be run remotely from home or from the office. It can be run in Windows or in Linux. It can be run in graphical mode or in the batch mode. The workflow is extremely consistent everywhere. So it's, yeah, there is definitely a very wide range of usability. The users receive quite a lot of working tutorials. There is now about 50 tutorials which are already working. They are based on real projects we did as a consultancy projects in the past. So there are real 50 existing workflows. Users can directly use them. There are 15 benchmarks where we are allowed to show them, which are comparing with the real measurement data. So 15 benchmarks available, public data, so users can make sure that TCA really works. And we also have good technical support. So yeah, it's one of the biggest benefits that we provide really good technical support, and our users are basically our family, and we help them to achieve their goals, and we do much more than just maintaining the software. We really help them with projects, if possible, of course. Okay, for the future, we will definitely be developing the T-opt module further. So now it's great, but we will continue developing it. We will keep pushing this TCAA module for acoustics. There are new benchmarks coming, and new features based on your requirements from the projects and from the real using software. And there will be completely new module which allow users to create their surrogate models called T-base. And yeah, last week we released the latest version, which is 24.10. It's really the best version ever. we have resolved a lot of bugs, and we added a lot of improvements, and added new tutorials and new features. We introduced it last week. There's also a light version of TCAE for those who have limited budgets. We allowed them to use CFD module, and little bit decreased our commitment. So the technical support is provided via technical forum. Otherwise, it's completely unlimited, and really accessible to really everyone. TCAE Lite, the light version costs a cup of coffee a day, so it's really yeah, accessible. And yep, this would be it from this introductory part, and I would like to ask Radek to get alert a little bit, and I will switch over the presentation to him, and let's see what he has for us today.
Okay, thank you, Luboš, for handing me the presentation, and just let me know if you see my screen.
So we can see it, yes.
Okay, perfect. And I will directly dive into the technical part. So I'm going to show you how the project to simulate acoustics on NACA profile is built, and I will show you some technical details, and mainly I will go through the workflow as it is. So just to introduce today's project case. So you can go on our webpage into the case study section, and there you find this NACA 0012 acoustic benchmark profile. So on this case, we tested and developed the whole workflow and the acoustic module itself. So here you will find detailed information about the case, about the topology, which I would like to present a little bit into detail, and we will show how the CFD simulation is preset. Mainly, we focus on the storing the acoustic data or data for the acoustics, and then we will go through the acoustic module setup itself, and maybe at the end we will show some outputs of this acoustic analysis. All right, so maybe I will directly go to the TCAA. So here I have opened the TCAA, for now empty, and I will load the project I have prepared for the webinar. So before weekend, I ran 2 simulations with the newest version on this NACA profile, and I will show you what we obtained. Okay, so I will open here. I have created the project. It's just testing project for the webinar, and here I have copied from my Linux machine the results from this benchmark or test cases, and so I will go through the results later on. So for now, I will load the project, and let's start introducing the workflow module by module. So Okay, so first of all, okay, maybe I haven't used the proper use a different function. Okay, so it doesn't matter. So it was I played too much with the case. Nevertheless, again, so the workflow consists of setting the module of T-mesh. So we need to preset the meshing. Then we go through the CFD simulation, and finally we can go through the acoustic module. So the topology of the mesh, because this is pretty project-like case, and the goal was to simulate the NACA profile. So for the acoustic purposes, so what does it mean? It means that we need to have a nice preset topology for simulating the NACA profile. Then we need to keep in mind that we need to simulate it in 3D, yeah, to capture all the details of the flow, and the simulation has to be transient, yeah, because acoustics needs the transient information. From the steady state simulation, you basically know nothing about the pressure fluctuation, etc. So these three main parts has to be taken into account. So first, to properly model the NACA profile, you need to have a large domain to get rid of the influence of boundary conditions. The second, you have to have 3D mesh, and you need to run it in transient, which means you need to somehow optimize the mesh count to be feasible to simulate it within a accessible or acceptable time framework. So these three items we need to care about. So therefore we suggested to have this big domain, which is split it into two parts to save a lot of cells in the resulting mesh. And when I go to the CFD geometry, let me just show you here. If I go visualize it as a surface with edges. So what we have here, we have two components. First component is the external one, which is created by structured hexahedral mesh, which is pretty coarse. Yeah, so because of we are simulating just the segment of the blade, small segment of the blade, to have really fine resolution of the mesh, but not to have dozens or hundreds of millions of cells. So we created this external block by just two cells in the width direction, and some kind of coarse mesh in the neighbor further from the profile. And the internal mesh here, it is a component 2. So we have the standard STLs, and the computational mesh will be created by the meshing, by the SnapX mesh itself. So we have two import data. First one is the external mesh, which we have created in the block mesh. Maybe I can show you very quickly how this can be done. And then we have the standard STLs, which defines our flow domain. So for this internal part. So I can go very quickly about the imports. So the external mesh is made simple with the block mesh utility, standard open form utilities for creating a simple geometries, structured geometries. So here we have a short script which we just define the domain size. So the outer sizing of the domain, and this cutoff area inside in the middle of the domain. So here we just define the coordinates. We define the thickness of the mesh. So it depending on the thickness of our NACA airfoil. So here we have the NACA airfoil has the dimensions of 0.4 meters in the chord direction, and the span is, I think, is something like 0.02, 20% or no 5%, sorry, 5% of from the chord. And this is also done because we would like to add also the serration, and the serration parameters definitely affect the sizing of it. So therefore these dimensions were generated. And here basically following what you need, you just change the parameters, the dimensions of the external mesh, you adjust the sizing of the cells. So for example, just to show you how it works, so if I would like to do the 1 meter in width, and let's say the sizing will be 0.2 in the Z direction. So to generate this mesh, we need to go to the standard, let's say, console. So I will open this TCE open for Windows shell. So this is implemented in Cygwin, which emulates us some kind of Linux command line and Linux environment. So let me just go to our working directory, which is on D drive, webinar, I think today's date, and it's called geometry and external block mesh ERI for testing. So now I am there, and now I need to just run the block mesh utility. And whenever the mesh is generated, you can then see basically directly I can click here and we can visualize the mesh, and this mesh can be then imported into our software. So here into the TCE. So sorry, here surface with edges, and this is my new setup. So basically by this framework it was generated, and here you can then go component 1. If you start from beginning, there is import. So if you import the mesh in open format, then you find the mesh you have created, and the mesh is imported as in here. The second component, for the second component, we have the standard STL import. So here then for the STL import, you then need to create the mesh parameters, the standard parameters. So we have this background mesh size. Then for each part of the geometry, so the geometry is split it into the 3 airfoil parts, so pressure, suction side, and the edge at the end. Then we have the interface, which connects the internal part with the external part, and then we have the front and back faces, which we connect by translation MA. So it's like periodic segment simulation. Yeah, so the STLs, you can create it by because we have just the airfoil at the beginning, so you can create it by your script or any CAD software which you have. On our side, we typically use Salome or any other open source code we like the most. And as an example, for example, here we have implemented a script for Salome, which loads some necessary parameters. It loads the NACA profile file, which looks standardly as the coordinates, XY coordinates of the profile. And at the end, maybe I can show you how it works. So if I open Salome, so the scripting interface pretty nice, because you can nicely script what you need to generate, for example, with respect to the STLs. So let me go to the webinars, today's webinar, geometry, and let me load this Python script. So now the Python script is evaluated. Also, you can run it on the background. So everything can be run from console, and I think now it's creating the surfaces. It triangulate. Yeah, okay, it's running. Triangulate the faces and create us the STLs, which then we can nicely import here. So in this way, we prepare the import data. Then we need to play carefully with the mesh. So we need to have proper mesh refinement. This is connected to the CFD model about the resolution of the flow. For the acoustics, you need to have really fine mesh and DS like, or the best one LES. But if you do not have so many resources to play with, so you can go for the DES at least to resolve all the fluctuation of the pressure which influence the final acoustics. So therefore the mesh refinement has to be pretty nice. Okay, yeah, back to the Salome. So now the Python script was finished. So we can just look what we have generated. So this is the example of NACA profile with the serration. And basically what we have, so we have automatically created such a domain. Each part is exported as STL, and just to visualize what we have, how it looks for the 1 meter span. So this is the profile or 3D model of the airfoil, in this case with the serrations. What is really advantage of the TCAE that, for example, you preset something for this geometry for the plane NACA profile, you run it, or if you create it, run it, and then you would like to repeat it, but for another geometry. So what you need is just to re-import the surface. So you can re-import the surface, go for example, the geometry with serration. So you see here STL, and you just pick the appropriate STLs to be replaced by the original one. And when I click it, so you can now see that the surface was just re-imported with the version with the serrations. So if I go here, 0.3, just to have some opacity, just to see that now we have imported the version with serration. We can save as different project and run it, and we don't need to change or check all the other parameters. And these we will have two simulation, which is face-to-face comparable with all the same meshing parameters, CFD parameters, TCA parameters, so we can then really compare face-to-face how this changes in the shape, for example, affects either CFD parameters like drag or lift, and also the acoustic parameters like this final spectra and the magnitude, basically the decibels of the resulting signal. Right, so this was about the meshing. So when you are fine with the mesh, so maybe let's see how the mesh looks like. So if I go to one of my computed case, so here, for example, this NACA plane profile, if I go to the T-mesh module into the CFD and here in the file cells, so we can read that we have altogether almost more than 6 million cells. And if you would like to see the resulting mesh, so maybe I can open the case. So let me load one of the computed case just to see the topology of the mesh. So we have just 5% span width for the NACA Airfoil 0.4, and we have 6 million cells, and this just is for this let's say webinar purposes. So we can imagine how demanding is to do the acoustics. So everything has to be perfectly set. The mesh has to be resolved fine, and you have days of simulations, and then you are able to get some results. So it's really for experienced users which knows how to create the mesh, how to run the CFD, and then you can go for here you can go for the acoustics. So it's not a piece of cake to simulate acoustics and have a good results. Okay, back to the mesh. So whenever the project which I've run for the weekend is loaded. So let me just show you how the mesh looks like. So yeah, show the final mesh. Okay, so it will take a while because as I said, we have 6 million cells in the overall count. And even though we have this topology that the external domain, which is really wide, I think 50 meters in here for 0.4 for NACA profile. So we save a lot of cells in the external part, and we focus just to mesh the internal part. Yeah, it's already loaded, so I need to click here to visualize the CFD mesh. And as you can see, which is a really nice view, if I use 2D and I will focus on the Z direction. So this is the topology of the mesh. So if I zoom, you can see this is the refinement along our profile. So if we zoom more, so this is how the fine mesh is for this, let's say, small object. Yeah, so you can imagine if you would like to simulate something bigger or fans, how many cells you would need to have a very nice resolution. So you can imagine how demanding the simulation is. All right, so this is our topology. We are okay with that, and we can go back to the setting the CFD simulation. So I will not go through all the details because it's, let's say, standard setup for the external aerodynamics. So we have, for the acoustic, we need to have the compressible model, yeah, to capture all the properties of the fluid. So we need to go for the compressible. For the turbulence, we have this variant K omega SST DS. Yeah, so we need to have this DS, at least DS like the hybrid runs less model. What I can say here about time management. So we run a steady state simulation just to initialize the flow for the transient. Here we run 0.6 seconds, and basically it's all the important about the CFD, but about the acoustics, what is new? If you go to the runtime evaluated quantities, here is the section to write the acoustics data. So here you ask to store all the pressure, velocity, density fluctuation for further acoustic analysis. So this is very important. And what is very big advantage of our implementation is that the data are stored. So anytime you can go back and, for example, do just the acoustic analysis. So with different parameters, with different observers, I will speak about it later. But everything is stored and it will remain on the disk after the simulation, and anytime you can refer to these data, and if anytime after the simulation is finished. So write acoustic data, then what we have here you can change the start time for storing the data, because typically in the initial phase, even it is initialized by steady state simulation, you need to let the solver to kind of converge to the period condition. Just for example, at the beginning it may appear some oscillation in the solution, and you don't want to include this oscillation into the acoustic analysis. So typically you skip some initial time for the simulation and you store just the last, for example, half or something like that, something similar. So here we tell, okay, we just want to store the data from 0.3 seconds. We wanted to store every time interval, so every time step, which is also important with respect to the frequency resolution and general of the resolution or the stability of the transient simulation. But here, yeah, typically you will want to store every time step to have a nice resolved information for the acoustics. Data format, here we implemented new, let's say, formats which are compressed and save a lot of space, because, for example, for this case, for this NACA profile on 6 million cells, where we store 0.3 second up to 0.6 second with the transient time steps equal to, sorry, I need to go back to the solver, 4 times 10 to minus 5 seconds. So with this small time stepping, so this case for the plane geometry, if I count almost 100 gigabytes of storage on the disk. So you can imagine how demanding for the storage this is, but then you for example simulate 1 week, 2 weeks, and then you have all the data to further analysis. Otherwise, if you lost something, or if you need to for example evaluate the signal for different observer, then you will need to recompute it again. But this approach, everything is stored, and you can recompute the acoustic part anytime after CFD simulation is finished. Okay, so here for binary tar, so this is a choice number 1 because it saves a lot of time, disk space. Then we have the surfaces, which is the acoustic surfaces. So on the surfaces, all the data needed for the acoustic analysis is stored, and from this is the source for the acoustic signal. Again, there are many more approaches. First approach could be, for example, take directly the data from the surface. And typically the second approach is to use so-called permeable surfaces. So it's some kind of surface which amongst somehow your object, which also takes into account for the fluctuation by the turbulence, etc. So the permeable surface is the second option, and anytime you can go for any combination, or you can add more acoustic surfaces and then analyze what is the source from the different parts, shapes of this permeable surface shape, and for example a distance from your object, etc. So this is also new, and then each of the surface can be taken for the acoustic analysis. For example, I have an example here of this permeable surface, which I put here into the STL permeable surface. So here I put 2 surfaces in the wake area, or above the trailing edge, which is the main source for the acoustic noise, and I place, for example, both from the suction and pressure side, and later you can play or distinguish which one will be choose for, again, for generating the signal. So these are new features, so you can combine any sources, any shapes, so combine with CFD patches directly, or external STL, or there is also built-in geometry, so there are some predefined shapes. By the shapes you can also create some virtual acoustic surface. All right, and that's basically all. So this is how you define the sources for the acoustic, and then if you are lucky and everything is set well, you just run the simulation, and at the end the data will be available, and by one click, so within a single project, you can also add the acoustic module, or you can create new project with only the acoustics module and load the already generated data. The data are always stored within the transient simulation of your project. So let me show you where. So if I take, for example, again this case, which is already simulated, so in the simulation run, the data are stored in CFD module, TCFD, because the data was generated by CFD simulation, by the transient simulation, and here if we can go to the post-processing, and here we have the directories which are named by the name we define within the acoustic surface. so permeable surface and airfoil. So for example, here we have airfoil surface, and here we have the data for the airfoil or for the permeable surface, and this for the acoustic. And when we go to the acoustic module, and the acoustic module is connected directly to the simulation, so you can check which one will be used for the direct, let's say, acoustic analysis within this run, within this whole TCA run, or you can create just the project which includes of the acoustic module only. So let me show you here, and I have created here. So you just create a new for the acoustic module only, and let me for example load this one. So you then have just the acoustic module enabled, and here in the simulation CAE analysis it looks like this. So you have surface 1, and you simply choose the format you have stored with the previous simulation, and here you just click select and go for the given data for the surface data. So if you go again post processing for example permeable surface, and then you select this file, and the file is loaded, it's checked, so it's loaded, and then you can run the acoustic analysis directly, or it can be directly run within this whole whole big workflow when you really start from beginning up, and it ends with the acoustic analysis. So then you can choose with the available surfaces. So this is about the source data. So anytime after the CFD simulation is done, you can go for new acoustic project, load different sources, and then basically we will have, for example, as I did, three project. First one, the big project which runs together with team mesh generation and CFD simulation, and it, for example, takes the data from the CFD patches, and then you will have 2 permeable surface. And for example, as an example, I also take just the permeable surface from the suction side only. I will explain later. So about the observers, so I think this is clear. You just place the position of the microphone. If you have some benchmark of the position of the observer where you evaluate the resulting signal from acoustic analogy, or you can create observer group, which can be created within a virtual circular distribution, which is handy for the final polar plots. I will show you in the report. Or you can have a list of the measured points within the CSV file, and this can be imported. Here again, we parallelize the code, so you can set as many processors as you have on your machine to speed up the acoustic analogy simulation. Anything can be scripted. The important physical constant like speed of sound in your environment and reference pressure for 0 decibels. The new feature is that you can evaluate the source surface frequency analysis. Sorry. So frequency analysis on the surface, or like phase of the emitting signal from the acoustic source surface. So you just choose which frequencies you want to see, and then these frequencies can be visualized on your surface. I will show you. Surface probes. So if you like to follow, for example, just fluctuation of the pressure at a certain position, or any other derived quantity, then you can ask for example, to compare with the measurement, because sometimes you can measure the fluctuation at the exact point within the domain. So then you can nicely compare them. Standard signal processing features, so how low high frequency filters to get rid of some unwanted signals in the source signal, and how to manage the fast Fourier transform. And the final is the report. So you just choose which parts of the report you would like to see and some kind of units you would like to see, and the resulting. And here you can ask for the frequency for the circle plot. So if you created the observer groups by the circular distribution, then you can ask for frequencies to be visualized and computed on the polar plots. So I will show you right away. So whenever the simulation is done, so then you have also, let's say, three main kind of outputs. So first, the biggest one is the report. So if I go, for example, for this plane, you can directly load it if from the project, for example, like here. So if you run it within the project, you will see the HTML report in the GUI. But anytime you can go back to any of the project directory and locate the report from it, directly from it. So if you go to the TCA module, here we have the report. I can open the report, and the report shows again some kind of basic statistic about the case, the observer summaries. So I have one single observer, so it will show you some overall sound pressure. You can also play the sound of this, so you can try on your own, on your side. I can't transfer the sound at the moment over the microphones over this webinar. But then you have the unfiltered signal and filtered signal, the source signal, the acoustic pressure for which is received by the observer, and then the fast Fourier transform on this signal to create a power spectral density or power or to generate a sound pressure level per observers. For the sound pressure level, you have the standard output of the Fourier transform into all the frequencies, and then we also evaluate the two different bandwidth. So this is the third octave bandwidth and octave bandwidth to see the signal or to compare it with other data or data from the measurements or from the another CFD simulations or acoustic simulations. And the final, yeah, here are the probes. So you can follow the probes densities or density probes pressure fluctuation at your defined points. And finally, we have the polar plots. So if you have the circular distribution, so for each point on this circular distribution, we plot the amplitude for the given frequencies. Yeah, so this is the position of the point, and on this axis, on the radial direction, there is the amplitude in decibels. And again, you can go through all the frequencies which were asked in the report section. Okay, so this is the report. And about the surface fluctuation, so we can go on the disk. So let's for example compare. Let's get again the plane. I will go to the simulation run TCA. The first point, if you have more transient point, it can be also evaluated, but we have just one point. And here surface pressure fluctuation, and you can open this surface FFT. So if I double click, I can click apply, and so this is our surface on the airfoil, and I can, for example, visualize this phase of the signal, and here you can choose which frequencies you would like to see. So this is the basically the cosinus of the phase of the source signal, and for example we can compare it with the results on the airfoil with the serrations. So if I go to the next project, so here I have the same simulated case, but on the geometry with the serration. So again, going to the acoustics module, to the result, surface pressure fluctuation, and again I can load the surface FFT, and maybe we can split the view, and into this view I will visualize the plane geometry, and into the second one I will visualize the serrations. Yes, and I can link the camera. So by right click, mouse click, I can connect the camera to have the same view, and I will also visualize the same quantity, and then you can nicely compare the frequencies and how around frequency the phase of the signal and how the serration affects the distribution for each frequency. Okay, anytime you can of course take out the or you can compare the sound pressure level for these two variants of the geometries, for example. So again, if you go to the TCA module into the figures, here you can see all the figures which are generated for the report, but you can take any picture of it. So for example, I will take the sound pressure level for the plane variant, and the same I can do with the serration case. So again, 30 figures, the same one, and you can face-to-face compare how the serration affects the overall signal. So you can see that typically the output of it is that decreases the signal, so it lowers the amplitude, and the volume of the signal from the airfoil with the serration is typically lower for the given frequencies, and in this way you can compare and, let's say, optimize the acoustics on your object by changing the shape in a proper way, and you can analyze how it affects the resulting acoustics. Okay, so maybe for now I'm fine with what I have shown you, so maybe it's time to go back to Lubos, and maybe Lubos will have some other notes or remarks to tell us, but for now let's conclude. And
Yes, Radek, thank you very much. Thank you for your part. It was it was great as usual, so thank you. So yeah, I would like to ask the audience to ask your questions. We really like to think what you to know what you think, and share our answers. So yeah, ask your questions. We are definitely moving to the end of the webinar. So now it's the space for questions. I have one question we received, which is concerning the time step. Radek, if you can elaborate a little bit on this, or what time step you choose for, because we are talking about highly transient simulations, right? We are simulating dynamic process in time, and the time step for CFD. What's are there any special requirements regarding the time step on acoustics and on stability of CFD?
Yeah, definitely. So if you can
Yes,
share my screen again, because it will be better to
back. Yes.
Okay, so about the time stepping, as I slightly mentioned, so you choose the time stepping here, and it depends. So it mainly affects two things. First is the stability of the transient simulation, and basically the accuracy, because the accuracy of the CFD solution depends on the time stepping and on the special time stepping, or the special step sizing of the cell, basically. And all this is also some kind of or it referred to also to Courant number, which tells something about the stability of the solution. So basically, so the time step has to be small enough to capture, the accuracy of the time resolution, also to capture the frequencies you would like to reveal within the simulation. So if you go to the report, it will show you the sampling frequency and basically the Nyquist frequency, which is somehow derived from it. So this is the, let's say, the highest frequency you can resolve within the CFD simulation. But also from the CFD point of view, you need to have fine enough time stepping to increase the accuracy of the solution itself. So this is mainly two parts about the time stepping.
Okay.
Yep. Oh, yeah.
Okay, Radek, thank you. Yep. So yep, that's time step. We have question from Anir, who is asking, but it's difficult maybe to understand. Well, if sound pressure exceeds threshold, isn't acoustic wrong? I don't know what threshold is meant here.
Yes. I am not also not sure.
So we would okay. So we would need
or
to specify.
Maybe let me check if maybe if we see that the decibels can be also below, but it can be right. So if the threshold is mean for the 0 decibels, but yeah, the signal can have negative decibels, but I think we don't know
could be
what
something even something else. Okay, so let's skip this. So but for formal reasons, we mentioned we would need more information of this question, and we don't need to answer it via email, right? Later to save some time.
Yes.
And okay, well, Anand is asking, was the simulation done by DES? So I just quickly answer yes. It's DES. We're receiving all the time these kind of questions about turbulence. Yes, it's definitely very important, and also it's all about the mesh, right? So if the mesh is fine, then all or many models are fine, and if the mesh is I would say coarse, then all the models are I would say difficult to apply. So it's a question, but it's the yes what we use here, and we recommend it, and the results we compared to measurements data seem to be good or acceptable in the range. Anand is also asking, how was the sound propagation modeled? So I think it's been mentioned. So we used analogies. Specifically, it's the William Hawking analogy. We used as a basis for TCAE module. For TCAA module, we used the library lib acoustics. So if you Google lib acoustics, there's online open source resource for OpenFOAM. And we have used it, and we have redesigned it, and this is really important, and here we differ from what's available. We store the data on the disk, so we save the pressure fluctuations. Basically, we save everything what's necessary, all the quantities that are necessary to be able to come back anytime. So we can come back anytime to the results and rerun the William Hawking analogy to make sure with different settings, with different distances, with different microphones. So we keep all the data. We keep them. We do not throw them away from during the simulation. That's we believe, we definitely are sure that it makes a lot of sense. So we store all the data, and we can come back anytime to them. And also Anand is asking, and perhaps this could be the last question of this webinar, and it's where the sound is calculated. So Radek, can you go for the last one?
Yes, definitely. So we sample the pressure and density and velocity fluctuation on the surface, on the acoustic surface, and from the source surface, the acoustic analogy is made to propagate the signal, which goes to the observer. Yeah, so it goes to the observer, which is defined here in the observer section. You can add as many observers as you want, and this acoustic analogy gives you the signal which goes from the source surface to the observer. And for example, here in the report, you see the final signal per observer. So this is the acoustic pressure in the microphone position, in the observer position, and from this acoustic pressure, the fast Fourier transform is performed to get the sound pressure level for each observer. So then this is the resulting sound pressure level graph or values, which basically gives us the information about the resulting sound signal in the observer position. And this is done for every position of the observer. So you will see these signals. So the answer is the last question, where the sound pressure level calculated. It's basically here in these positions per observer you defined. So
so there are predefined positions, locations in space, which are called observers, and there we evaluate the signal.
And they are defined by the user, of course, because
sure,
knows the position. Yeah.
Okay. So I think this could be it. We don't have any other relevant questions. So let's conclude. We would like to thank you for your attention. It was a pleasure for us to present. Of course, as usual, if you have any questions, feel free to contact us. We will gladly talk to you. We will gladly answer all your questions and concerns and issues, and really be sure that we are aligned. And then you can freely decide if it makes any sense for you or what. So so thank you everyone. Thank you for your time. Radek, maybe.
Yeah, thank you for watching. Take care, and looking forward for your questions or any contact with us.
We leave you with that, and bye bye for now.
Bye bye.